In this section we're going to look at a number of special types of primes. We'll start by defining Mersenne primes and Fermat primes. These are numbers that are one more and one less than a power of 2. We'll look at Pepin's primality test for Fermat primes. We'll introduce Sophie Germain primes, and then look at Lagrange's divisibility test for the Mersenne primes. Okay, so what are Mersenne and Fermat primes? So any number that is one more than a power of 2, that's a prime, is called a Fermat prime. And any prime that is one less than a power of 2 is called a Mersenne prime. There's a lot of remarkable properties that these numbers have. For instance, all of the largest known prime numbers are Mersenne primes. Having this special form gives us more power to discover properties about them. So we have a little lemma that gives us a necessary condition in order for such a number to be a prime. So in part 1, a number of the form 2 to the n plus 1 is a prime only if n is a power of 2. And then a number 1 less than a power of 2 can be a prime only when the exponent is a prime itself. So in part 1, why must n be a power of 2? Well, suppose n had some odd prime factor. Suppose n has an odd, doesn't have to be a prime factor, just an odd factor, m. So say n is m times k for some k and z. Then if I'm looking at 2 to the n plus 1, I'll write it like this, and think of this as being an mth power, where m is this odd number. So it's 2 to the k to the m plus 1. And we know how to factor anything of the form x to the m plus 1. So if this is an odd number, then x to the m plus 1 has x plus 1 as a factor, and so I can just pull off the x plus 1 part. So I'm thinking of x as being 2 to the k, and then we're just left with what, x to the m minus 1, like that, together with this alternating sum, 2k m minus 2, and then plus, minus, plus, minus, and you go all the way down till we have a plus like this. So it's just a basic factoring formula for a polynomial of this type. And the same thing holds in part 2. So what's our conclusion then? So if n had an odd factor, then we'd have this type of factorization here, and that would tell me that this is a proper factor of 2 to the n plus 1. So thus 2 to the n plus 1 is not a prime. In other words, if 2 to the n plus 1 is a prime, we couldn't have a situation where n had an odd factor. And then in part 2, so we want to show that if 2 to the n minus 1 is a prime, then n itself is a prime. Well, let's suppose n is not a prime. Suppose n is not a prime. Say n equals a times b for some positive integers a and b strictly bigger than 1. Okay, so a and b are both bigger than 1. Then when I look at 2 to the n minus 1, that's 2 to the ab minus 1. And it doesn't matter, just pick either one of these values. I'll say it's 2 to the a to the b power minus 1. And now think of that expression as an x to the b minus 1, where x is 2 to the a, and we know how to factor this polynomial. It's just x minus 1 times x to the b minus 1 plus x to the b minus 2, dot, 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 all the way down the road until we just get a 1 at the end. And once again, we see that 2 to the a minus 1 is a proper factor of 2 to the n minus 1, so 2 to the n minus 1 is not a prime. Therefore, in order to be a prime, you cannot have a factorization of this type, so n itself must be a prime. Now, unfortunately, this is just a necessary condition. It is not going to guarantee that we have a Fermat or a Mersenne prime. So let's look at the Fermat numbers. So having identified that in order to be a prime, the exponent must be a power of 2, we'll introduce this notation f sub k to be 2 to the k power plus 1. So these are the only types of numbers that have a chance of being Fermat primes. So for a general k, we'll just call it a Fermat number. And then for the Mersenne numbers, the exponent has to be a prime, and so we'll define m sub p to be 2 to the p minus 1 whenever p is a prime, and we'll just call that a Mersenne number. So the first few Fermat numbers, f sub 0 is 3, f1 is 5, f2 is 17, f3 is 257, and f4 is 65,537. And it can be shown that all of these numbers are primes. So certainly 3, 5, and 17 are. 257 just takes a little more work to verify, and 65,537, you could use one of the tests we did last time to verify that this is a prime. So based on this evidence, Fermat made the bold conjecture that all numbers of this form are primes. And he wasn't able to deal with the next number in the list because they grow extremely rapidly. The next number would be 2 to the 32nd power plus 1, and it was too difficult for him to try to factor. Then came along the human calculator, Euler, and Euler took a look at f5 and was successful in factoring it. So Euler showed that Fermat's conjecture was false by simply factoring the number 2 to the 32nd plus 1. And I'm going to let you do that as a homework problem because there is a theorem you can prove that describes the type of prime factors such a Fermat number can have. So any prime has to be one more than some multiple of 2 to the k plus 2 power. So knowing this description, you can, with a little trial and error, find some prime factors of f5. So I'll let you work that out. Well, not only was Fermat's conjecture false, we have now quite the opposite conjecture going on. So it has been tested for k equaling 5 through 21 and shown that all of these Fermat numbers are composite. So the new open problem is whether there exist any more Fermat primes. So none have been found beyond the first few that I listed already. Pepin's primality test gives us a simple way to test for when a number is a Fermat prime. It says the following. So we have two conditions, that Fk is a prime and A is a quadratic non-residue is equivalent to the single condition that A to the Fk minus 1 over 2 is congruent to negative 1 mod Fk. Now one direction is trivial and we've already done it, and that is that if Fk is a prime, then by the Euler criterion we have A to the Fk minus 1 over 2 is congruent to negative 1 mod Fk if and only if A is a quadratic non-residue. So the really interesting part, and I've indicated that right here in the statement, the really interesting part is the converse. So I want to be able to show that something is a Fermat prime. So we start with some base A, and if for that base A to the Fk minus 1 over 2 is congruent to negative 1 mod Fk, then I get to conclude that Fk is a prime. So with a single application of the type of test we were looking at last time, we get to conclude that a Fermat number is a prime. And I claim this is just an application of Lucas's primality test. So how did the Lucas test work? We first have to calculate A to the Fk minus 1. Well, part 2 tells us that A to the Fk minus 1 power is negative 1 squared, which is plus 1. So we have the relationship of Fermat's little theorem holding, and then you want to look at any proper divisor of Fk minus 1. So D not equal to Fk minus 1. Well, what is Fk minus 1? Fk minus 1 is 2 to the 2 to the k plus 1. That's the kth Fermat number, and you're subtracting 1. It's just a big power of 2. So if I want a proper divisor of this, it's a power of 2, and so that would mean that D is a factor of 2 to the 2 to the k divided by 2, and so I'd subtract 1 of 2 off from it. But what does part 2 tell us? Now part 2, we have this exponent, Fk minus 1 over 2. Oh, what is that equal to? That is exactly this value right here. And we've just said that A raised to this power is congruent to negative 1. And so if A to the D was congruent to plus 1 mod Fk, that would imply that A to this power, because D is a divisor of this power, is also congruent to plus 1. A contradiction. Therefore, A to the D is never plus 1 mod Fk for any proper divisor, and so the order of A is in fact the full order. And the conclusion we get in Lucas' primality test is this implies that Fk is a prime. The second part in part 1 is trivial, because now that we know that Fk is a prime, it follows from Euler's criterion that A would be a quadratic non-residue if part 2 is holding. So we have a test for Fermat primes right here. There's a connection between Fermat primes and regular n-gons that Gauss observed. We're not going to prove this. This is something you would do when you study Galois theory. So he proved the following theorem. Suppose I want to construct a regular n-gon where n is a prime number. Then you can construct it with a straight edge and compass if and only if n is a Fermat prime. So the first few Fermat primes were 3. And I think you all remember how to construct an equilateral triangle with a straight edge and compass. The next Fermat prime is 5, and that gives us a pentagon. And then you have a 17-gon, which I wouldn't want to try to describe. And then the next couple were at 257. 217, then 257, and then the 65,537. And believe it or not, people have actually sat down to do those constructions, etc. So those are the only regular n-gons that can be constructed with a prime number of sides. Now you all remember that with straight edge and compass, you can bisect angles, and by bisecting angles you can therefore construct objects with twice the number of sides. So you can get a hexagon very easily. You can get a 6, you can go to 12 then, or you could go to 10 sides, or 34 sides here. So it's very easy to double the sides. So the general theorem that Gauss discovered goes like this. A regular n-gon can be constructed if and only if n is a power of 2 times a product of distinct Fermat primes. So it's a nice characterization of when we can do these straight edge and compass constructions. Let's turn now to the Mersenne primes. So the first few Mersenne primes, remember the exponent has to be a prime itself. M2 is 3, that's a prime. M3 is 8 minus 1, which is 7. M5 is 31. M7 is 127. And so far we are 4 for 4. So the first 4 primes yield Mersenne primes. However, when we get to p equaling 11, M11 is 2047, which has a factorization. So it's not true that MP is always a prime. And the reason M11 fails is that 11 is a Sophie Germain prime. So what's a Sophie Germain prime? So any prime Q such that 2Q plus 1 is also a prime is called a Sophie Germain prime. So they are named after the mathematician Sophie Germain, who was studying them in connection with Fermat's last theorem, the x to the n plus y to the n equals z to the n equation. So it was established in the 1800s that the Fermat's last theorem, which was really a conjecture at the time, was valid for Sophie Germain primes. So here are a few examples. There's lots of Sophie Germain primes. So 2, if you go 2 times 2 plus 1, that's 5, which is a prime. 2 times 3 plus 1 is 7. 2 times 5 plus 1 is 11. 2 times 11 plus 1 is 23, and so on. So all of these numbers have the defining property. And so it's natural to ask, well, it looks like we have an infinite collection, but this is an open problem. Are there infinitely many Sophie Germain primes? Open. We can be a little more precise if we want to count how many Sophie Germain primes there are up to n. Let's call that Sn. The conjecture is that that number is asymptotic to a constant c times n divided by the square of the natural logarithm of n. or this constant, is about 1.32. And if you look at the data set, you can see how accurate this conjecture is coming out to be. So up to 100,000, we have 1,171 Sophie Germain primes. The asymptotic estimate is 1,166. And you get up to 1 billion. You've got agreement almost to 4 places. And up to 10 billion, you have agreement almost to 5 places. So again, the asymptotic symbol means that the ratio of these two quantities approaches 1 as n goes to infinity. So it's very likely that this conjecture is true, just based on the evidence here. Okay, this is an interesting test for the Mersenne numbers. So not only will it reveal that a Mersenne number is composite, it actually yields a factor. It tells us an explicit factor of the number. So it goes like this. Suppose Q is a prime congruent to 3 mod 4. Then 2Q plus 1 divides the Mersenne number MQ if and only if 2Q plus 1 is a prime. That is, Q is a Sophie Germain prime. So that's why the prime 11 failed when we looked at it earlier, why MQ was not a prime. It's because 11 is a Sophie Germain prime, and 11 is congruent to 3 mod 4. So in the case where we have a Sophie Germain prime and Q is greater than 3, it follows that MQ is composite. Now the reason I need Q to be bigger than 3 is why. So if Q equals 3, then M3 equals 7, and 2Q plus 1 is 7. So it's not given us a proper factor. Proof. So we have two directions. Let's suppose first that Q is a prime congruent to 3 mod 4, and that 2Q plus 1 divides MQ. So we want to prove that 2Q plus 1 is a prime, so we do a proof by contradiction. Let's suppose 2Q plus 1 is composite. I'll let R be a prime factor of 2Q plus 1, and let's let it be the minimal prime factor of 2Q plus 1. So it's a composite number. Do its factorization as a product of primes, and I'll pick out the smallest prime factor, R. Well, then R is a divisor of MQ. That's just transitivity. So R divides 2Q plus 1, and 2Q plus 1 divides MQ. So it's a divisor of MQ. And why is R squared less than or equal to 2Q plus 1? That's because 2Q plus 1 is a composite number, so it has at least 2 prime factors, and little r is the smallest. So it can be at most the square root of this quantity. So R squared is at most 2Q plus 1. Now R being a divisor of MQ means that 2 to the Q is congruent to 1 mod R. Why is that? Well, MQ, you've got to bring back the definition, is 2 to the Q minus 1. That's the definition of the Mersenne number. And this is congruent to 0 mod R if R is a divisor of MQ. And so 2 to the Q is congruent to 1. Well, if 2 to the Q is congruent to 1 mod R, then the order of 2 is a divisor of this exponent Q. Now, Q is a prime, and so it doesn't have a lot of divisors, and therefore the order must in fact equal Q. It can't equal 1, and it's a divisor of Q, so it must equal Q.
Well, what type of group are we living in? We're in the group of units mod r here, and that's a group of what order? Well, little r is a prime, so this is a group of order r minus 1. So any element has an order dividing r minus 1, so q must be a divisor of r minus 1, which means q is at most r minus 1. Or in other words, that r is greater than or equal to q plus 1. But that contradicts the fact that r squared, way up here, is less than or equal to 2q plus 1. Let's see, why is that? If you went r squared here, you'd get q squared plus 2q plus 1, so we can't have r squared to be smaller than this part, because q squared is some positive quantity here. And we got our contradiction. Therefore, 2q plus 1 must be a prime. Conversely, we now suppose that q and this prime p, defined to be 2q plus 1, are both primes with q congruent to 3 mod 4. Well, then p is congruent to 7 mod 8. So I just put in a number of the form 3 mod 4 here, so it'd be 3 plus 4k, and add 1, and you can see 7 plus 8k, we get a number of the form 7 mod 8. So since p is congruent to 7 mod 8, the following is true. 2 to the q is 2 to the p minus 1 over 2, by definition of q. Then by the Euler criterion, this is the Legendre symbol, 2 over p, which is congruent to 1 mod p. And where is that coming from? This is from the fact that p is 7 mod 8. So we know how to evaluate the Legendre symbol 2 over p. So we've got 2 to the q is congruent to 1 mod p, which means that p is a divisor of 2 to the q minus 1. That is, p is a divisor of m sub q, the qth Mersenne number. QED. Exactly what we wanted to prove. So, these are the first few Sophie Germain primes that are congruent to 3 mod 4. 11, 23, 83, 131. And so for these primes, we can conclude that the Mersenne number MQ has the corresponding factors 23, which is 2 times 11 plus 1, 47, 2 times 23 plus 1. So if I'm looking at M11, which is 2 to the 11th minus 1, what is that? 1024 times 2, 2047. That 2047, not only is it composite, but it is divisible by 23. 23 times some k. And that M23, 2 to the 23 minus 1, is divisible by 47 times some k prime. So not only are they composite, we actually are given factors of these numbers by this test. Now it's an open problem whether there are infinitely many Mersenne primes, although all of the largest known primes are Mersenne primes. So let's just talk a little about the history of that. So in 1876, Lucas discovered a record-breaking prime number of the form 2 to the k minus 1, with k equaling 127.
Now that's remarkable in
pre-computer time. He discovered a very clever algorithm for a test in primality of Mersenne type numbers like this. In 2008, the 45th known Mersenne prime was discovered at UCLA. It's a number right here with how many digits? Over 12 million, almost 13 million digits. So it's the largest explicitly known Mersenne prime at that time. And the finders of it earned a $100,000 prize. So there is prize money for discovering record-breaking big prime numbers. And this was the first one, I think, that exceeded 10 million digits, and that's why it earned a $100,000 prize. So today there are currently 48 known Mersenne primes. The largest one was discovered in 2013. I don't think they gained much prize money on this one, but it's one with 17 million digits right here. If you're interested in being part of the search, check out the GIMP's website, the Great Internet Mersenne Prime Search on the Internet, and you can participate in just running these algorithms. If you have a PC sitting idle and you want to try to search for the next record-breaking Mersenne prime, you can join this project and try to win some prize money.